There we go. Okay, so we're going to have a brief review and then go into some applications. Piezoelectric and IEPE technology, these are common terms used in piezoelectric. And in the piezoelectric field, the sensor does not have electronics in it, whereas in IEPE, the integrated electronics piezoelectric, the sensor does have electronics in it. So we're going to be focusing mainly on the piezoelectric style of sensor in this presentation. But basically, you have a very wide measuring range. You have the ability to range the measuring chain. You have the ability to do quasi-static measurements as well as dynamic. And you have the ability to reset and tear the system from static mass as well as switch between measure and operate, or measure and reset as well. The frequency response of a piezoelectric sensor is often characterized as a lightly damped second-order system, which you see here on the high frequency side. On the low frequency side, it's typically characterized as a single pole high-pass filter. Some of the rules that are useful when developing fixtures and measurement systems is trying to understand exactly what the usable frequency range is relative to a piezoelectric instrument. Well, that can be related oftentimes by the natural frequency, where the 5% or 10% natural frequency band is just either 1/5 or 1/3 of the natural frequency. And what I mean by 5% or 10%, that's where the amplitude response varies over frequency by either 5 or 10%. So if you had a unity input and you had a 5% frequency range, your output could be, say, 0.95 to 1.05, for example. And then also, just as a review, considerations for force dynamometers. I mean, the dynamometer is often used in our measurements because it can take on non-axial forces. It can calculate forces and moments. It basically absorbs moment loads and distributes the forces amongst the sensors. So it gives us a very powerful means of developing measurements of some complexity for large and small test articles. Obviously, the dynamometer arrangement, the geometry can be various shapes and sizes: square, triangular, rectangular, circular, which you'll see a few of those throughout the presentation. Some of the things just to keep in mind is that the analog bandwidth considerations basically are determined by the charge amp, from a minimum and maximum level, what's possible. The test article obviously tells us what we need to do our to do our analysis, to do our measurements. And then lastly, the force sensors and fixtures that are developed basically try to achieve the test article requirements. And sometimes that's easily done, sometimes not so easily done, depending on the application. So there's often trade-offs involved with making decisions. For example, on usable bandwidth might be increased to accommodate a certain frequency range, for example. We went through considerations on the last part, and such as installation and mounting, what the top and bottom plate needs to be, the tolerances, the materials, what the load-bearing surfaces need to conform to. Obviously, linearity is one of the major error sources in force measurement. How we select sensors and what the preloading is, and how preloading helps us get the best out of our fixture. Ground isolation and noise considerations. We're going to hear a little bit more about noise in part two. Certainly, sensor alignment and crosstalk is always an important. No sensor is perfect in terms of crosstalk, but having a good alignment gives you the best possible result. Calibration and checkout is rather critical, using either dynamic methods or static methods, or perhaps a press that's got some calibration capability or calibration references integrated is also another option. We reviewed mass loading effects on dynamometers. Basically, dynamometers are spring mass systems. They're going to act in that way. And basically added mass will reduce natural frequency. So it's often important to take consideration on that. The frequency response questions and stiffnesses and how that relates to performance, and obviously making FEA analysis to confirm designs. We're going to touch a little bit upon vacuum operation in this presentation, as well as environmental considerations as well. So one thing I didn't mention in the last presentation, which I think is important, because as we add test articles to our dynamometers or to our force sensors, our test articles in themselves can have some height, some width, some dimension that has to be at least recognized. And what I wanted to point out is that in the classical four sensor, say rectangular or square dynamometer, we had these set of fixed expressions, but in this set here, I've added a correction factor, the KMX, KMY, KMZ, which are basically correction factors due from calibration. When moments are applied with a lever arm, there's a non-ideal stiffness of the dynamometer, causes an uneven loading over the dynamometer. So what you get effectively is a virtual increase of sensor distance. And so what the calibration attempts to do is reconcile or resolve what this difference could be and make a correction factor out of it by taking the calculation and comparing it to the actual measurement during calibration. You can derive these calibration factors. It's an important point, especially as test articles increase in size, say in height, might be a factor that we want to take a consideration in terms of the moment correction factors. What I wanted to do here was just point out that this is a typical calibration certificate, and what you see here is in the moment areas, there would be a separate coefficient or adjustment coefficient or K factor that would be allocated. And what's important is, going back to this diagram, is that the calibration needs to be replicating exactly what your real world example is, in terms of the offsets of your center of gravity and with regard to the sensors themselves. So this can all be definitely quantified or defined and then made into a calibration if needed. So what I wanted to do then is go into a little bit on measurement noise considerations. Obviously, electrical noise. We talked about ground isolation, and this is an inherent attribute of the three-component force sensors that we talked about, as well as the dynamometers. Avoiding strong electromagnetic fields, always good practice in using shielded cables. Anyway, from Kistler, the cables are all 360 degree shielded, providing good resistance to EMI. Battery power, we're going to touch upon, is another way to reduce electrical noise. And obviously the AC power conversion to DC is somewhat of a noisy process. So using battery sort of eliminates that. And as we talked previously, bandwidth is directly proportional to our RMS noise. And that's always a factor, is to understand the analog bandwidth that you need to make your measurement work. Some of the other things that we're going to touch upon is, probably in the area of microvibration, is the transmissibility of seismic inputs, obviously structural response of the test rig, acoustic borne noise, HVAC. There's other factors when you're trying to measure down to millinewtons and so forth. You need to have identified your environment and made a test stand that actually gives you some resistance against the environment and is protected from acoustics and so forth. So we'll touch upon that as well. In terms of noise, I think we're all pretty familiar with the time domain relationships and how a noisy signal could look from, say, a sine wave to something quite noisy. But in the frequency domain is really where we find out a little bit more about the noise profile. So what we can do is we can define a noise power spectral density, and this is typically in, say, microvolts per root hertz, or it could be micronewtons per root hertz, depending on what a sensor sensitivity is. And then what you can do is you have a frequency allocation as a function of this noise power spectral density. So what that enables you to do then is define what noise you might have in any given frequency band. And the RMS noise is basically the integral of the noise power spectral density over a given frequency band. So whenever we talk about noise, it's always important to ask, well, what frequency band does that relate to? And for sure, FFTs are extremely helpful in our analysis because they give us basically a bank of narrowband filtering where we can really optimize on bin widths based on sample rates and number of FFT points and so forth to get say favorable signal to noise ratio on a bin basis and perhaps even supporting higher resolution of measurement for the phenomenon that is of interest. In terms of DC power, I give an example here really of a charge amp where what we did was we, on the 2 picocoulomb range is the most sensitive range of a charge amp, sorry about that. And 2 picocoulombs means that 2 picocoulombs equals full scale. So if you had a force sensor, say of 4 picocoulombs per Newton, you would have a half a Newton full scale in your measurement. So that's quite precise. Full scale means plus or minus 10 volts. So in that scenario, you would have an additional, say, 8 or 9 dB signal to noise ratio if you used a battery powered amplifier versus, say, just using an AC powered supply or AC powered supply. So what that tells us is that at the most sensitive regions of the charge amplifier is where we have to take probably the most care in terms of the electrical noise as well. What I show here in this picture is not a 2 picocoulomb example, but say 100 picocoulomb, where the green curve is really say the noise profile for a battery-powered charge amp, and you do see that the 1/F noise is definitely lower, and certainly this would be more profound in the 2 picocoulomb setting. You can also see that there's 60 hertz, or it's US based, but there's 60 or 50 or 60 hertz noise or harmonics, and these can be eliminated further with battery power, or your data acquisition system should run off of battery power as well. And then you would see that these fundamental frequencies of line power would actually be much less, if not eliminated totally. So battery power is an important tool if you need to get the best performance out of your system. One other consideration I wanted to mention is that the way you construct forces and moments, okay? We talked last time about a summing calculator in a charge amp, and this is quite powerful, okay? In micro vibration applications, there is an added noise because there's this summing calculator is actually an analog circuit with gain and so forth. So you're going to get some additive noise there. The lowest noise scenario would be to take the 8 channels output of the amplifier, put them right into your data acquisition system directly, and use a software to calculate the forces and moments. So this is done with a software called DynaWare, certainly that's used quite a bit in test and measurement arena. And it's fairly easy to use, and you just define the A and B offsets of the sensors relative to the center lines of the dynamometer. And this gives you the results fairly quickly using the software. So you do get a lower noise solution at that point. The other thing I wanted to mention is harmonics. A lot of things that are devices that are measured are going to have harmonics associated with them, and a lot of times you're interested in harmonics for a lot of reasons. It might be that you want to better characterize, it might be a pump, for example, or it might be some rotating mechanism, and you want to better characterize it to understand how to reduce the harmonics. Obviously, harmonics can excite fundamentals or resonances in a spacecraft that would be of importance. So that would be certainly a compelling reason to better understand harmonics. harmonics are basically integer multiples of the fundamental, and as such, it's going to really push out your frequency demands on the dynamometer or on your force measurement system. So it's often good to understand what your harmonic requirements are and then feed that into your requirements on the force measurement side. And again, you can use these rules that we established earlier relative to the natural frequency and the 5% and 10% frequencies. As far as the vacuum measurements go, there's a call for vacuum measurements in a lot of different measurements. I mean, cryocoolers obviously can be acoustically noisy, and sound transmission does not travel through a vacuum. And with thrusters and propulsion, you would get a higher thrust level in a vacuum because the gases are overexpanded, which produces the higher thrust. So there's many reasons why you'd want to do a vacuum test on your test article. What's critical there is really to have a dynamometer or a force measurement system that is low outgassing, as well as a cable. And with vacuum chambers with a high vacuum, you need a vacuum feed through. In this case here, this is a multi-pin Fisher feed through, vacuum feed through. And this would then interface with your conventional instrumentation that would be typically on your bench doing the work in your lab. Obviously with vacuum testing, what's important is low outgassing cables and solutions. And a lot of times low outgassing can be guaranteed by a manufacturer, and indeed that's very important. A lot of times, regardless of the guarantee, it's important to perhaps do a bake out. Okay, and this might be a standard practice at various companies that just want to eliminate any possibility of outgassing. So the bake out looks at elevated temperatures in a vacuum environment over some specific time interval, and then monitors that to ensure that you have a low outgassing result. Sensors themselves, hermetic sensors, tend to be already low outgassing because there's a very low. And usually what's done is a gross and fine leak checks at the welds are the most critical points, and you can quickly determine if you have a very good weld and that you have a low outgassing sensor as well. In terms of the installation guidelines for a microvibration, a typical installation would be that you'd have a pneumatic isolation. You'd have a stone table or perhaps an optical bench, adapter plates, piezoelectric dynamometer, another adapter plate in the test article, and then actually some noise protection would be also somewhat important. In terms of pneumatic isolation, this basically gets you isolation from the seismic inputs from the environment. Stone tables are known for their very good natural frequencies, especially using a general rule of 10% rule, which says that the test article and all the fixturing on the table is less than 10% of the mass of the table. We have found that this gives very usable natural frequencies of the table as well. And in terms of the adapter plates, usually we recommend a stainless steel adapter plate, perhaps on the order of, say, 25 to 38 millimeters thick, obviously ground flat and parallel, and having adequate holes to accommodate the dynamometer mount, as well as the interface to the table itself. So it might, if it's an optical bench, there's usually a very dense mounting hole pattern. If it's already a granite table, there could be another mounting hole pattern already in there. But anyway, you always want to make sure that the mounting holes of the dynamometer to the adapter plate have sufficient fasteners around those locations onto the table itself to get the best natural frequency. And this was talked about in the part 1 session. I think we covered a lot there. The adapter plate on the top is typically, we can recommend aluminum usually. In that, I think is a good compromise to have a low mass on the dynamometer, as well as largely there's not usually a lot of bending moments associated with these types of mechanisms. This is one example that we made recently at one installation where we were using a fairly large optical bench initially, and the optical bench had to be maybe 3 to 4 meters long and maybe 2 meters wide. It's quite large in a clean room, and we had found that the noise, and we had turned off the primary air handler, and we were seeing this black curve is actually a reference that we got from another institute. And we were in the order of that black curve, okay, with the primary air handler turned off. But actually going to a granite table in an anechoic chamber, we were able to achieve up to, 1 to 2 orders of magnitude lower noise, which is quite profound. And certainly, the granite block is certainly is a very sound approach to making microvibration measurements. The optical bench, at least in these cases, had some sensitivity to airborne acoustics, which was notable, but it still was quite usable. This noise floor, although it was quite a bit higher than this noise floor, was actually still quite a bit lower than what the actual test required. So it was actually still quite favorable to do the test in the clean room for this one test that was being performed. It's always important to do a background noise check in your installation to ensure that you've quantified noise levels and as a function of noise sources. Obviously, if you have an anechoic chamber, this will give you probably the best result right from the start. We talked about previously micro mechanisms, but there's a multitude of mechanisms that go into the testing of exported force and moment testing. And we're going to touch upon a couple of these in the next few slides, but the same concepts of force measurement can be applied to a lot of these mechanisms. So we'll just touch upon a couple. One is a reaction wheel, and reaction wheels are very, very common nowadays because they're reliable, and they actually allow attitude correction of a satellite without any use of fuel. And this is actually quite critical, obviously, to longevity of a satellite and mission performance. Now, because the actual reaction wheel has a motor, electric motor, and a rotor, it's a rotating mechanism, and it's going to have a jitter associated with it based upon the balance of this rotor as it spins at various rotational speeds. So a lot of times what people are doing is they're trying to understand and characterize how that operates as a function of rotational speed over frequency. And what happens is, when the actual attitude control system has such a jitter, you can get actually blurring of an image. You have a different pointing. Your pointing of the satellite can be actually affected adversely. So this red spot might be the requirement, but you're getting some larger deviation due to, say, an unbalanced reaction wheel, or perhaps there's other devices on the satellite that are also contributing to a poor pointing. So fundamentally, the exported force and torque testing really wants to be used to characterize, but also to help balance the reaction wheel as well. This is a typical setup that you would find in terms of a reaction wheel test. And we talked about this microvibration dyno. It's a ceramic top plate dyno, really optimized for high frequency. There's very good noise profiles in terms of broadband RMS noise, in terms of less than 1 millinewton, and certainly less than 1 millinewton meter as well, on the order of 4/10 over a broadband frequency of up to 10 kilohertz. And what you see here is examples of a static imbalance and a dynamic imbalance, where you're actually doing what's called a waterfall plot of force, rotational speed versus temporal frequency, where you would see this would be the static imbalance, and then you'd have the dynamic imbalance with moment, where the primary ridge is usually associated with the static or dynamic imbalance of the rotor. and then you would have harmonics perhaps of that, and then also contribution of, say, bearing and rotor out in higher frequencies as well. These types of waterfall plots really assist in characterizing the performance of a reaction over its full spectrum of operation, and also it's being used in order to assess or determine is balance adequate? Did it get properly balanced, or how to balance it? So it's used in many aspects in that regard. The other example I want to show with reaction wheels is what I want to go back here and point this out. In this type of solution, you have a large dynamometer and you have a calculation. So you're calculating forces and moments based upon that fixed set of expressions that I spoke of earlier. In this example, this is about I don't know, about a 65 millimeter OD, and it's about, I don't know, maybe 100 millimeters high, but it's actually a 6-component force and torque link. So there's no calculation whatsoever. It's got force and moment capability integrated in, and using reaction wheels mounted directly to the top give pretty much the same performance as you would see on the classical dynamometer. What I just show here is an example of one rotating at 500 radians per second, and you can actually see the sinusoidal offset due to the imbalance in the wheel. So it's just an example. But these systems tend to have a very high natural frequency, and they're individually controlled. So there's no cross coupling between forces and moments. Each axis is independent. So it's quite a powerful tool for force and torque measurement, especially exported force and torque testing. We had one example from one installation where a customer was looking at ways of improving signal-to-noise ratio at the lowest rotational speeds. And concept was evaluated with an optical tachometer, where you would coherently integrate the signals as a function of the angle or of the wheel itself. So this basically gives you an improvement in signal-to-noise ratio. Coherent integration is often known to do that, and certainly you can expect that you would get on the order of, say, a factor of 3 to 5 improvement in signal-to-noise ratio, and that in itself is quite a powerful tool as well. And a lot of times rotational devices can be quite repeatable, and though they have noise, they're repeatable in terms of what the profile is. So integrating it helps bring out the sinusoidal imbalance profile. Then we also can talk about satellite cryocoolers. Cryocoolers are often used for cooling detectors, and there's a lot of different technologies being used. Stirling, pulse tube, Joule Thomson would be some. Obviously, with vibration disturbances by the cryocooler are usually attributed to the cryocooler compressor, and pumps and so forth are usually the main contributors to vibration. But in these mechanisms, they tend to have also harmonics, which could excite the spacecraft resonances, as mentioned previously. So understanding performance, say up to 500 hertz or maybe even up to 1,000 hertz sometimes, is a requirement. So having the right force measurement system is quite critical to evaluate harmonics in these cases. And obviously, exported force and torque testing is what's typically used in these types of measurements. What I wanted to show here is some work being done, and it's a bit still ongoing, and there's going to be a paper written from Utah State University Center for Space Engineering. Dr. Swenson and Anderson and Joel Mork have put together a test bench and evaluating the ATA architecture for a 6U CubeSat cryocooler satellite. So what I want to do is just review some of the preliminary results of that, and there'll be a paper written in the next few months here. So basically, the cryocooler is a closed loop circulation of helium gas to the cold finger, And then there's a thermal strap which connects to the detector. And this is, at least in this case, was a PGS material and provides high thermal conductivity and high flexibility. The optical detector obviously is cooled by this process. There's actually, what's not shown here is there's an evaluation of wire rope isolators, which you'll see in some upcoming slides. And these are basically braided stainless steel assemblies. The heat exchanger, pump, and rotating fluid joint and radiator panel basically are being used to get the heat out and cool the cryo cooler as well. It circulates this Novak 7000 heat transfer fluid at about 4 to 5 bar. We have found that this process is actually quite noisy. There is also a particle damper at the cold finger, which at the cold tip, which really is used for lower operational vibration as well as launch survivability. And it's usually comprised of small steel particles that are allowed to freely move in some reservoir. What was found is that a 50% fill was actually quite effective in terms of attenuating some of the vibration there. And obviously the radiator panel is a motorized assembly, where typically the edge on of the radiator panel is typical to minimize heat loading to the sun. So what I wanted to show here was just a couple simple examples while you see the video here. So basically, this is a 3-component load cell, 9347, attached to the, say, a detector or at least the thermal strap right here. And this is actually the cold tip, and there's an accelerometer on top, 8763. And beneath everything is a dynamometer that's being used to measure the exported force and torque of the entire assembly. You can see here is a particle damper on the cold tip. And this picture here illustrates some of the axis conventions. The y-axis out of the dyno is usually around the connector. You have the x-axis is orthogonal to that out of this side, and the z-axis is vertical. In this case here, the vertical axis is up and down, like the z-axis of the dyno, and you have the displacer axis and the compressor axis of the cryocooler. So this is just a bit of a blow up here. I won't go through each piece, but it just shows how the entire assembly fits into the 6U bus of the cryocooler or of the CubeSat system, and it gives you a perspective of the size and magnitude of this development. What I want to show here is just some examples, and instead of showing, I mean, there's quite a few plots and quite a bit of data taken. I'm going to focus mainly on, say, the final results with full assemblies. Like I said, we found that the pump and the cryocooler were the most noisy contributors to exported force and torque. And what you see here is there's also I didn't show the let's see, I wanted to show the wire rope isolators. They're hard to see, but they're right underneath here, right underneath each assembly and also the detector assembly. So what you see here is really the result of a lockdown assembly, which is the black curve, where you see fairly high levels of vibration in the displacer, compressor, and vertical axis. And you see what happens when you have the floating isolation due to the wire rope isolators. It absolutely reduces the exported vibration down substantially in force and certainly in moment as well. And this is the exported moment. This is a full up complete cryocooler assembly, and you can see it's quite profound in terms of the reduction due to just using passive isolation in terms of this, in terms of the wire rope isolators. In this case here, at the cryocooler assembly, at the cold tip, we found that we found that actually the wire rope isolators were not as effective here. And it contributed to what analysis was done is the wire rope isolators actually had some amplification below, say, 100 hertz, and above 100 hertz were less were where you achieve the attenuation. So some of the frequencies that, the primary frequencies of the cryocooler were actually very close to this, 100 hertz or less than 100 hertz. So we were seeing definitely some amplification of these disturbances. And obviously some more work is being done in terms of particle dampers and more integrated solutions to reduce the overall vibration at the cold tip. But it gives you a flavor for what type of work has been done. Also at the exported force at the force sensor, this is at the end of the thermal link. At this point here, at the lower picture, you see that you get the same type of reduction with the wire rope isolators. We saw a very profound reduction in disturbance for all cases. So that was quite encouraging. Then we're just going to touch upon stepper motors and pointing mechanisms. Antennas themselves, are usually gimbal based, and you are pointing them. A lot of times, stepper motors are being used due to their high reliability and functionality for this type of a measurement. What we do is we use the same type of a system in terms of the exported force and torque system that we used elsewhere, and with the antenna system mounted right on top of the dynamometer. What we found was, because antenna systems tend to be fairly lightweight constructed, that the stepper motor themselves had actually in a normal and fast mode operation would actually excite the natural frequencies of the structure, of the actual antenna structure. So it certainly it was a very useful test to go through, seeing how the effects of stepper motor motion can affect the overall jitter or exported force and torque of the antenna system itself. And obviously, it's a very good tool to use in the R&D side to ensure designs are within the envelope of operation that's needed. I wanted to just talk briefly on satellite release mechanisms. And I just wanted to point out quickly that satellite release mechanisms basically are short duration transient events. And because of that, there's a much different type of requirement there. And you have to look at the frequency range is usually proportional or inversely proportional to the duration of the event. If you have a rounded event, or say a half sine event versus a rectangular event, your frequency demands are going to be different. Okay, and the sharp rectangular event is going to have much higher frequency content out in frequency, whereas the rounded event, a half sine event, is going to have a much lower frequency content. So if you see here, general rule of thumb, where say a total energy would be is a 99% bandwidth of a rectangular pulse is around 10 times the inverse pulse width, whereas for a half sine pulse, it's typically on the order of the inverse of the duration of the event. So if you had a 1 millisecond event, I mean 1/1 millisecond is 1,000 hertz, for example. So you can see that the magnitude of frequencies can be quite large depending on what your transient event is. And obviously that feeds into your force measurement design. What I wanted to point out is with transient event tests, you need to make sure that your transient event bandwidth is not is lower than the natural frequency of the test of the dynamometer or fixturing. If it's not, you're going to get basically a coupling of your actually event that you're trying to measure with the natural frequency of the system, and there'll be really no way to filter that out. So you really want some separation. So transient events will put added demands on your force measurement system, where you really need to have separation between the event itself and the bandwidth of the system, or in the resonance of the system. Just to go to force limiting quickly, and I see I'm got about 20 minutes left. Just to point out, the life of a payload going into space is actually quite quite dynamic in terms of liftoff and launch, and finally flight and deployment into space, as illustrated by this one picture. And you can see here fairly high level vibration at the initial part of the launch sequence. This is just an example of some actual test data from the GLASS mission, which actually shows actual accelerations measured and forces measured. And sorry, this is in pounds. It didn't convert that over to newtons, but the conversion ratio is just multiply everything times about 4.5, and you'll get the number of newtons involved. But you can definitely appreciate that the amount of force and vibration during launch and flight can be quite substantial, and certainly need to be factored in to the test of the test article. In environmental testing of payloads, there's quite a few factors that come into play. I mentioned a few here: shock testing, vibe testing, force limiting, vibroacoustics, thermal vac, electromagnetic compatibility, all very important. In terms of force limited vibration, the key there is that force limiting automatically notches the acceleration at the test item resonances by measuring and limiting the reaction forces between the test article and the shaker table. So there's actually a dynamometer located right on the shaker between the test article and the shaker system. And this technique actually replicates fairly accurately the actual response of the test article in flight. The actual mount typically being used is a compliant system. So whereas shakers tend to have a very high mechanical impedance, and it's really not a representative way to test a satellite itself, is to have a shaker just putting energy into the satellite. The force limiting replicates, because of the monitoring the fixed base resonances, replicates the actual amount of the payload. Pretty interesting. Extremal control is being used, and there's several suppliers who do control systems for force limiting, where they're monitoring various forces and acceleration and coming up with control limits based upon flight data analysis and safety margins. Typical example here out of this NASA report is just showing how, if you didn't have a force limiting solution that notches at this frequency, you would get a substantial input into the structure, which could damage the structure or damage the test article, or even worse, make it inoperable. This is an example of a work done some years ago at NASA, and what you see here is basically the GPM satellite, and it has a fairly big observatory, has a fairly large force ring, using a very thick 76 millimeter top and bottom plate. Ring diameters around 2.6 meters, using fairly 12 load cells and custom bolts for preload. Just a picture of what this might look like is really this circular dynamometer. And what you can do, much like I showed in the part 1 session, is you can easily compute closed form expressions of forces and moments based upon these offsets, and quickly derive your closed form expressions. And this is just an example of what you might use as just a rough estimate for allowable forces and moments. You can take the number of sensors. You can look at the maximum shear forces allowed and axial forces. Use the number of sensors and a safety factor, typically a factor of 2. It's quite useful to come up with guidelines and maximum shear and axial forces. And you can do the same thing with moments, and certainly overturning moments as well, just to get an overview of what a specific design might give you as an initial calculation. Actually, with PE force sensors, it's a rangeable solution, as mentioned before, and certainly the stiffnesses of sensors increase as capacity increases. So there's a lot of work being done to also model the force ring and determine the resonant characteristics by FEA as well. So quite a bit of analysis with regard to determining the correct fixture for the test. As far as preload goes, I just show some examples here on preload, but basically what preload does for 3-component load cells is it's going to give you linearity, it's going to give you compressive and tensile force handling capability, and it'll give you the ability to measure shear forces. Because the sensors themselves has a frictional coefficient of about 0.2, you get a 5-to-1 ratio preload to shear force handling capability, which is quite profound and allows a wide range of testing without any slippage possible. I talked about this earlier in terms of part one, in terms of a dynamic checkout, where you would actually dynamically vibrate or shake the test fixture and maybe a mass simulator below the first resonance, and do a apparent mass calculation to check out and calibrate the test article in situ. Obviously, static masses can be used, but they're very cumbersome, and especially with large test articles, large rings. Not as common, certainly. In terms of what's out there in terms of capabilities for real-time control, the M+P system I show here just as an example. There are others. Real-time control of and calculations of forces and moments. You can do vector notching, force notching, overturning moment notching. All can be done with every channel of the force measurement system going into the data acquisition and controller, which is probably the most general solution to have without any pre-summing in front. Also, what's being used out in the industry is a analog method using Stanford research componentry. Now, this probably isn't widely used. For sure, it's not. And it's used mainly when controllers don't have the capability for calculations. Because if you remember, these moment expressions have sums and differences and multiplications. So basically what these pieces do, these elements do, is they create an analog circuit or analog representation of this expression. So you've got scaling amps, you have the sum difference amps, and this allows you to actually derive analog signals with very low latency that can drive a controller if the controller can't make the calculation. In some cases, this concept is being used for to cross-check calculations being made by these sophisticated controllers that I talked about. This is just one example of a test. I mentioned the LabAmp platform earlier, and the LabAmp is actually quite powerful in that it's a dynamic charge amp being used for actually force limiting. It wouldn't be used for a preload, at least the 5165 wouldn't be used as a preload. It would be a separate amplifier for preload. But basically what you see here is the actual every analog signal going to a data acquisition shaker controller. And what's really powerful is that the LabAmp actually supports background or backup calculations as well, because it's an integrated data acquisition system on top of being a charge amp. It gives you that benefit as well. So just on the Ethernet to be able to stream the data right to your disk drive and record the data as a backup. I'll touch upon thrust testing briefly. We have about 10 minutes remaining. There's been quite a bit of advancements recently in electric space propulsion, and certainly the chemical propulsion is an area that I think has been present for many years and certainly quite used nowadays as well. Certainly chemical rockets have lower specific impulse, but high thrust, whereas the electric propulsion or ion propulsion engines typically have higher specific impulse, higher efficiencies, and lower thrust. So there's absolutely a comparison to be made between the two technologies. Certainly it's something to keep in mind in terms of whatever type of propulsion test is being done. Obviously, piezoelectric solutions have some benefits. Strain gauge solutions have benefits. So it's good to understand technologies as well. With propulsion testing, you're going to have certainly the requirement for thrust measurement. And as I said, it might be a piezoelectric force or strain, but also you want to characterize thrust. It could be a static and dynamic pressure measurement, and as well as dynamic pressure, high temperature dynamic pressure measurement to measure the combustion process. So, and then also vibration measurement might also be a requirement in terms of the propulsion test stand. What we're going to do in this session is not go through each area as much as just talk mainly on the thrust side, the thrust measurement side. And certainly we talked already about vacuum measurements. I'm going to touch upon thrust misalignment because this topic comes up from time to time. Obviously, vertical and horizontal orientations have different demands in terms of bending moments and calibration and crosstalk, so those have to be addressed. And actually, thermal isolation. Whenever you have a rocket test, you always want to be sure you thermally isolate from your force measurement platform. I wanted to touch upon strain gauge just briefly. Strain gauge is a widely used technology. Basically, it could be used for pressure sensors, load cells, torque sensors, and certainly I've seen it used quite a bit in the thrust measurement area. Certainly, it operates on a concept of deflection, and the deflection that it measures in terms of the strain gauge bridge is going to have a change of resistance, and that resistance will be proportional to the load. Okay, so it's definitely a different concept to piezoelectric, where piezoelectric operates on a stiffness concept, where it's typically optimized for high frequency and dynamic, and whereas strain gauge is optimized primarily for static and that's gives you at least some choices in terms of your measurement platforms. I just wanted to touch briefly upon PE and strain gauge technology. I mean, this is often a hard thing to do because it's always application dependent, as to what is better or worse. But I try to take a shot at or attempt at this anyway, just giving a flavor for what might be favorable for one technology, maybe less favorable for another technology. As you see here, there's no one technology that does every measurement in the world. It just doesn't work that way. So there's definitely benefits to technologies. And piezoelectric, like I said before, is very stiff. It's rangeable. It's you can tear the system with regard to any initial loads, so you can really optimize on the dynamic side. This is absolutely important with all the applications I've talked about up to this point. You basically, although the force platform has a load on it, the actual measuring range is based upon the dynamic portion, not the static portion. Sensor dimensions tend to be small, and so forth. It has a very good overload profile, and so forth. And in terms of strain gauge, pretty much ideally for static forces, optimized for that. Very good temperature compensation because of the resistive bridge and being able to compensate using thermistors. Good cable properties as well as good accuracy properties. So for sure, there's decisions to be made in terms of PE and strain gauge technology. And a lot of times strain gauge is really the one that's been used over the years for static long duration measurement. Because as I mentioned before, piezoelectric can have drift associated with it, and certainly if it's a low level force, drift will be more prominent. For high level force, drift often is insignificant to the thrust measurement. So it's absolutely an option for some scenarios and some applications for sure. I talk to a lot of people out there doing thrust measurements, and I just wanted to take a snapshot of the piezoelectric side because I find that in the industry there's quite a bit of awareness on the side of strain gauge. And so on the other side, I ask users, hey, what would be interesting points to bring out, from a strain gauge to a piezoelectric measurement. And certainly what's brought out to me anyway is strain gauge is a much lower natural frequency, and it's viewed as inherently noisier from a mechanical noise perspective. It's got a lower stiffness, and certainly the test article mass further would reduce that natural frequency. So I think that's definitely understandable. It's a flexure-based system versus a stiff system based on stiffness. So definitely reasons to understand that comment from users. Certainly response time, what some users have told me is that the fast acting events really require the bandwidth, and what they observed is that with some strain gauge solutions they've used is they've seen some mechanical filtering of the waveform by virtue of the measurement tool. So it's something to keep in mind. And then obviously test stand adaptivity is really the other one is because piezoelectric is a rangeable system. You can configure it. One test stand can be configured for a multitude of test articles. So it can be obviously calibrated for each range. We talked about full and partial range calibrations. We talked about building up dynamometers, so it could be a force link dynamometer. It could be something that's built on site based upon components. And certainly the low crosstalk is actually another area that was brought to my attention from some of these users, and some of the things to keep in mind. Anyway, there's a good awareness on the strain gauge side, and at least for a range of applications, for sure, the piezoelectrics provide some capabilities as well. I wanted to point out in some of the experiences I've had with strain gauge, the dual redundant force sensors or single and multi-component force sensors are sometimes used. Certainly, strain gauge offers dual redundant. You can also do dual redundant or stack up force sensors with piezoelectric. A lot of times you can just sum these and actually get double the sensitivity, but you can also get a redundant sensor for sure. Obviously, shunt calibration is very, very common to strain gauge measurements, but it's not possible with a piezoelectric. So certainly similarities and differences for sure between the technologies. This is just a quick example of a custom dynamometer with a thrust stand where it integrates in not only the dynamometer, but also pressure sensors for dynamic pressure of the combustion process, as well as static pressure for control of propellants. You can see here that you can use these fixed expressions that we talked about earlier with charge amps, and data acquisition could readily give you the 6 degree of freedom solution for these types of tests. One thing I wanted to mention here, just one example is, in the industry, obviously you're always concerned about astronaut safety. And one of the things being done with the NASA Orion program, or SLS Heavy Lift, is having the ability to have an abort system where you can save the lives of the astronauts if something adverse were to happen. What I wanted to show here was just a quick view on an application where it's a attitude control motor test. And in this case here, you have 8 propulsional valves equally spaced around the abort rocket. And what you see here is that it has 2 functions to steer the abort system from the crew module away from the emergency, or orient the capsule. Okay. I guess that didn't work so well. Or orient the capsule so a parachute deployment can be made. So yeah, that was supposed to show you the actual test, but you have actually a picture here of the firing. On the base of this on a test article, you actually have a dynamometer made of piezoelectric sensors, force links, going into a charge amplifier to derive the 6 components, forces and moments. So just an example of what can be done with piezoelectric, but we'll have to get that video improved. And one last comment I just wanted to make on thrust misalignment. I get questioned on this. I'll say not a lot, but certainly the questions come up is, hey, how can we measure misalignment? Misalignment is a challenging application. Okay, a lot of times, you can use two methods. You can use a method of measuring the side forces, or you can use a method of measuring the moments. Okay, and what we determined was measuring the side forces actually result in lower uncertainties associated with measuring misalignment, and where the moments themselves, measuring the moments, had a much higher uncertainty associated with it. So at least that's on this one example is what our conclusion was anyway. Um, and usually the inherent alignment of rocket motors, or maybe it's a thrust vectoring application, but a lot of times in these applications you're using standard dynamometers. It could be, or it could be even a custom dynamometer that's built on site, or so forth. So some of the considerations here anyway. I just go through a few. Crosstalk. Typically selecting instruments with low crosstalk sometimes will get you very good results, and that's what we would do in this case here. Linearity also is a selection parameter. A lot of times linearity is a small percentage of the full scale range. The sensitivity of a long lever arm, F, X, and Y. When you have F, X, and Y at the nozzle, there's a long lever arm there, so you get a difference in sensitivity. Calibrating that out is very important. So having a calibration test stand that represents the motor itself can get you down to a very low error in the sensitivity with regard to that force application point, or where the nozzle location is. Certainly the effect of crosstalk on the variation of the FZ application, doing an allocation on that, and sensor individual sensitivity variation with FZ force uncertainties. So all these factor into the overall uncertainty of the measurement. Obviously, you have to make sure your temperature isolated from the thruster, because piezoelectrics will be responsive to that. Flatness, we've already talked about the importance of that, and also interfacing the thruster to the dynamometer itself in a very rigid way is also very, very critical to the measurement. So what we did by this calculation is we were able to get to about a 23 Newton uncertainty, where our budget was around 30 Newtons. So that was definitely within the budget range that we established. Just as a summary here, and I know I'm a few minutes late, sorry for that. Anyway, we went over a lot of topics in part one and part two. And without going through each one, I think there's a very good representation of some of the considerations, practical considerations to make in terms of using piezoelectric instrumentation. I encourage you to look at part one session if you weren't present, and certainly if you have any questions at this point, I'm happy to address them.
Thank you very much, Bill, for this intense session. And to everybody, feel free to still ask your questions via the Q&A box. We will answer a few of them right now, and all the other questions will be answered via email in the next days. So, Bill, first question for you. We had a couple of questions on the micro vibration setup, and it's it's mainly about the table underneath the dynamometer. What experience you have made in substituting the stone table with stainless steel block or with marble block? What's your recommendation on the material?
It's a good question. I know there's been some, there's probably been a little bit of work done on that. I think it's important I think what's most important is that it be very flat and parallel to the dynamometer. So the surface finish needs to be definitely there. What I worry about is with steel is some of the resonances that could occur. And I don't see marble being used very much in the industry at all. And even that, I don't see steel being used. It's either a granite, or I'll say the optical bench, which is probably more of a steel design, but that also has sometimes active and passive damping to be able to provide the natural frequency profiles that are sufficient for the measurement. So I would say I don't have any specific recommendation, but we'll take an action on that and survey our internal group here to see if there's a recommendation we can make. So we'll definitely send you a follow-up email on that.
Thank you. Next question on reaction wheel testing with our 9306 force torque sensor. How far, respectively, how many times could the size or the diameter of the reaction wheel exceed the sensor size?
Those are always good questions. I would say it's application dependent, but you really want to be careful about making something too big, because then you can actually get a wobble component due to the rotation. I probably wouldn't go more than I don't know. It's about about a 60 millimeter, 65 millimeter. We'd have to look at it for each case. I would tell you that. So please ask your question to your local person, but I probably wouldn't go more than maybe a 10 millimeter OD on top of that. But I would say please ask your question to your local person, and we'll be sure to give you some advice on the application, the weight of the device, how high it is. Those are the things that I would also want to factor in.
Next question is on the K-factor correction for a dynamometer. Mm-hmm. How can moments of inertia of large components be taken into account?
Yeah. I think in this case here, I don't really have an answer right off the top, but I'd be happy to answer that offline.
All right, then a more generic question. What is the influence of a changing ambient temperature during a measurement when it's about the accuracy?
Well, transient temperature response is one of those things that aren't spec'd. Okay, so what I would recommend is you actually do a test with the profile and actually look at the actual force profile. So this is the best way. Every transient event is different. Okay, it's hard to generalize. However, you'll see in dynamometry and force sensors that we do characterize the static or quiescent temperature performance, over the temperature range of the device. So if you were to change the temperature and bring it up to a steady state, you would have then a constant condition. The sensitivity would change for the device, and that would be probably the primary factor that would be included. But when you have a changing temperature during a test, you're going to potentially have a contribution from a transient point, but there's also a thermal time constant issue as well. Is how quickly does the actual thermal time constant of the test mechanism or test stand actually get influenced by that temperature? So there's several questions, I guess, that we'd have to look at. But I would suggest running a test and actually measuring it and quantifying it.
Okay, then the last question for today's live session. It's a very specific question on the active thermal architecture setup. And the question is, what's the influence of the natural frequency of the irradiator? Does it affect the test result? And if it does, to what extent?
We did not see a substantial contribution, at least on the test that we showed there. We did not see a substantial contribution due to that radiator. Now, with that said, yes, if there's a natural frequency that has a substantial and it's excited, you're going to definitely get a component that's going to be additive into the structure. We did not see that, but I would say as a short answer, yes. I mean, it would definitely couple into the overall. But what we found in this test anyway was the pump and the compressor or the cryo cooler were the primary contributors, and we were seeing upwards of probably 2 to 4 newtons of exported force, for example. So the actual motor associated with the radiator was actually a low contributor, and I don't recall if the natural frequency of the radiator was not a strong contributor as well.
All right. So having that said, thank you very much to all of you for joining that session. A special thanks to Bill for that inspiring session on space applications. I'm sure we will do more webinars on that topic in the future. Again, just to repeat, we will answer all questions via email. Everybody will get the recording of this session. Some of you have reached out to get the recording of the first session. If you forgot to reach out, reach out and answer to the email we're going to send to you if you still want to have the recording of the first session. I'm wishing all of you a really great day and looking forward to welcome you to one of our other webinars. Thank you and goodbye.